Welcome everyone to day 5. I'm out sick today, so I'm going to try and walk you through this from home. Homework tonight, we got day 5 problems. You can put in that in your planner. You can be checking your homework answers. That's all of them there. Now, while you are checking your homework answers, 2 things will be happening. One, if you could have your problem set out to be collected by the sub, make sure your name is on it. I will give you a new problem set the next day I am back. It's not going to be due till the Friday after break, so we'll wait to give you that until I am back. Also, the sub will be passing out the notes packet for today, and that can be found in the manila folder under the blue folder up on the front table. Okay, there's a paper clip or a rubber band of all the notes packets in the manila folder there for today, labeled AP 7-5. So while those 2 things are happening, okay, we'll give about 3 minutes or so, check each of your answers, and then kind of like we did about a week ago, I will kind of freeze on each set of worked out solutions, and then you can tell the sub if you'd like them to pause it or not on those solutions so that you could look at the answers more thoroughly. So we'll give you 2 or 3 more minutes to check these answers, and then we'll start looking at the worked out solutions. And in that time, hopefully you'll have turned in your problem set, and you'll also have gotten your notes packet and checked all your answers. Now, it's important as you're checking these, make sure you have the proper justification for them. Okay, not just diverges or converges, and we'll see those proper justifications when we flip the slide, and we'll do that in about 40 more seconds. Okay, so we're going to go through the worked out solutions. Again, I'll talk briefly about each of them. If you need more time, once I'm done talking, I'll let you know when I'm about to change. Have the sub pause so that you can look at it further if needed, and then the sub can hit play again to start it going once you're set. So there's our first few. You were just looking at the exponent. They were all p-series. If your p-value is between greater than 0 but less than or equal to 1, that was a diverge. Anything bigger than 1 was a converge. Okay, so I'm going to switch. So I thought the easiest way to figure out some of these, because many of them, especially the first term, was similar for so many of them, was to punch in several numbers, see what they started giving you. You could see which ones were growing more quickly and less quickly, and then that could determine which was which. So you had A, D, B, and C. I'm going to switch for this one. So we first wanted to find our partial sum of the first four terms. That's where that fraction or the 1.036 comes from. Then we wanted to see what our error or our remainder was. So we do our integral from 4 to infinity. When you go through and do that, you get 1 over 1024, which is approximately 0.001. Now in 44, it's the other type of question we see for that from our integral test day, is we want to know when is the remainder going to stay less than or equal to 0.001. So we pick some variable, often you see capital N, to infinity for our integral. We go through, do our integral, and then we solve for capital N. Now remember, this answer should always be capital N greater than or equal to something. So you just got to be careful with your sign as you're going through, and we needed it greater than or equal to 4 million, which already was a whole number. So 4 million would be the first one that would work out. Sorry, I forgot to tell you I was changing on that one, so I'm going to change. If you need to pause this still, go ahead and pause it. "57, geometric, R was less than 1, so converging. 58, geometric, R was greater than 1, so diverging. And 59, by the nth term test, our limit as n goes to infinity was 1, because square root of n squared is absolute value of n, but as you go to infinity, that's just going to be n, so really we're approaching 1. So we're diverging by the nth term test. I'm going to go ahead and switch. So two ways you could do this. The first way I showed is actually the more complicated way. So if you look at the groupings of terms, where I have the 0, the 1/8, 2/27, and so on, it's positive, decreasing, and continuous, so you could do integral test. So on the left there, I showed going through and do an integral test. You get 3/2, so it converges by the integral test. The easier way was to recognize that both of those things individually are convergent p-series. So therefore, their difference must also converge. I'm going to go ahead and switch. In 61, if we did limit as n goes to infinity, it's 1 plus tiny to huge. That's just e, so it's not approaching 0 as n goes to infinity, so diverges by the nth term test. Natural log of n is going to go towards infinity, so that also diverges by the nth term test. I'm going to go ahead and switch. All right, so hopefully by now you have your new packets for today. Today's topics, we're going to learn 2 more tests, the direct comparison test and the limit comparison test. Now keep in mind, the first page after our unit calendar in the packet has a list of all the tests we're going to learn in the unit. So you have that there as a reference sheet you can be working on as you're doing homeworks and things like that. So a little scenario. Let's say based on his height, Joachim is considered a giant. And based on her height, that Mitzi is considered a little person. Some things we know. Wendell is taller than Joachim. Preston is shorter than Mitzi. Mrs. Kushner is shorter than Joachim. And Amanda is taller than Mitzi. So for Wendell, we can conclude that he must be a giant. Because if Joachim is a giant, anyone taller than Joachim should also be considered a giant. So that's why Wendell can be classified as a giant. Now, if Mitzi is considered a little person, anyone smaller than Mitzi should also be considered a little person. So because Preston is shorter than Mitzi, then Preston must also be a little person. Well, I should say, by the way, so I'm using the completed notes from last year for this. So each time I get finished talking, I'll tell you when I'm going to switch the slide. And just like the homework, if you need it paused so you can copy down more, you can just have the sub pause it so you can write down the rest. Now, Mrs. Kushner. Mrs. Kushner is shorter than Jaquim. Well, if Jaquim is a giant, we don't know anything about people that are shorter than Jaquim. We just know the people bigger than Jaquim must also be a giant. And if Amanda's taller than Mitzi, well, we just know the people smaller than Mitzi should be a little person. So Mrs. Kushner and Amanda, nothing we can conclude. I'm going to switch slides. So here's a little visual that I found online that I think can help describe this. Let's say Will Ferrell, who's right here, if you don't know who Will Ferrell is, let's say we considered Will Ferrell a giant. We could then also conclude that everyone that's taller than him must also be giants. Anyone, if we're going just off of Will Ferrell being a giant, we can't conclude anything about the people less than him. Okay, but anyone taller than Will Ferrell would also be considered a giant. If we go to this end, what if we said Tom Cruise here was a little person? Then we could conclude anyone that's smaller than him would also be considered a little person. So all these people here. So if the only thing we had was that Tom Cruise was a little person, we couldn't say anything about the people above him. So that's just a little visual about what we're talking about. And we're going to do it in terms of convergence and divergence. So if you have something that diverges means gets bigger, then we can conclude anything that is bigger than it will also diverge. If you have something that converges, so in other words is getting smaller, we can conclude anything smaller than it will also converge. So that's where we'll apply it with our series. So what this is called is the direct comparison test. So say you have some sequence A of n that is definitely smaller than B of n. If the bigger one converges, the smaller one has to also converge. So if you're shorter than a little person, you're a little person. If you have that, again, that A of n is smaller than B of n. If the smaller one diverges, you know anything bigger diverges. So when something diverges, you know everything larger than it's going to diverge. When something converges, everything smaller than it will converge. I'm going to switch slides. So let's say we have this series and we want to know if it converges or diverges. Well, let's take a basic series that we can determine pretty easily. So what you'll always do is you'll say compare to. So we're going to compare it to the series of 1 over 3 to the n. This is an n right here, by the way. It kind of looks like an r, which we know converges since it is geometric with absolute value of r being less than 1. Something we know is true is that 1 over 3 to the n plus 2 is always less than 1 over 3 to the n. And let's think about why that is. If we put in 2 for n, 3 to the n would be 9. So on the right there, we'd have 1/9. But on the left, 1 over 3 to the n plus 2 would be 1 over 11. 1/11 is smaller than 1/9. If you make the denominator be bigger, the value will be smaller. So that's why we know the actual series we want is smaller than the 1 over 3 to the n. Well, if 1 over 3 to the n, if that series converges, we know everything smaller than it should also converge. So we can say by the direct comparison test, our original series that we had also converges. So I'm going to switch slides. If you need the sub to pause it to finish writing down, you can have them pause it. So here's just the visual. Okay, we can see that both of them converge. The 1 over 3 to the n plus 2 is always less than the other one, but they're both converging. All right, let's look at another one. We want to know if it converges or diverges the series. Well, let's pick a basic series that we know how to work with. So we're going to compare to the series of 1 over n cubed, which we know converges because it's a p series with p greater than 1. Okay, that's what we saw last class. Well, if we're adding 1 to the denominator, that's going to make the value of the fraction smaller. If we put in 2 for n, on the left we would have 1/9, on the right we would have 1/8. 1/9 is smaller than 1/8. So because 1 over n cubed converges, everything less than it will also converge. So we can say by direct comparison test, our original series there must converge. So I'm going to switch to the next slide. If you need more time, just yell out for the sub to pause it until you are done copying down everything from this slide. All right, so again, we want to know if this converges or diverges. So we're going to compare it to 1 over square root of n. Okay, that's a basic series that's similar to it. We know it diverges since it's a p series where p is greater than 0 or less than or equal to 1. Well, when we add 2 in the denominator, we've seen in other ones, that's going to make it smaller. Well, if 1 over square root of n diverges, the only thing we can then determine is things bigger than that will also diverge. So therefore, direct comparison test using 1 over square root of n will not work in this case. We cannot make a determination about things smaller than something that diverges. So we are going to need another test. So I'm going to switch the slide. If you need time to finish copying this down, just yell out for the sub to pause it. So don't worry about this yet. We're going to come back to this. This is just a visual of the two of them. We're going to come back to this slide in 1 second. So the thing we're going to use is the limit comparison test. So what the limit comparison test says, if you've got two series where the terms are positive, and when you divide them and take their limit as n goes to infinity, you get a finite positive number. So we're saying that L has to be greater than 0. Then we know both series will either converge or diverge. If we divide them and do the limit as n goes to infinity and we get that finite positive number, basically our unknown series does the same thing that the nice series will do. And it doesn't matter which one you do on top and which one you do on bottom, because if you do the reciprocal of something that's a finite positive number, it'll still be a finite positive number. So let's go back in the space we have on the previous slide, and we'll test out the one from before. So we're going to divide our 2 that we had here, the 1 over radical n plus 2 divided by 1 over radical n, and when you do keep change flip, we will get this. They have the same degree because they're n to the 1/2. So the ratio of our leading coefficients is just 1, which is a positive finite number. It's greater than 0. So we can say since our nice series, 1 over radical n diverges, since it's a p series that is p greater than 0 but less than 1, we can say that our new one, the series 1 over radical n plus 2, must also diverge by the limit comparison test. So when you divide the 2 and do the limit as n goes to infinity, if you get a positive finite number, then we know it's going to do whatever the nice one does. If the nice one converges, this one converges. If the nice one diverges, this one diverges. So I'm going to flip to the next slide. If you need the sub to pause this, just shout out for them to pause it. So something nice we would maybe compare this one to is our harmonic 1 over n, which is 1 over n to the first. We know this diverges because it's a p series. But like if you put 2 in for n, you get 1/2. If you put 2 in for n in the original, we'll get 1/7. Well, 1/7 is smaller than 1/2. So by direct comparison, we would need something to be bigger than the harmonic if we were going to be able to use direct comparison. So that tells us we should look for limit comparison. So we can divide the 2. So say we took the not nice one divided by the harmonic. When you do a keep change flip, it'll end up looking like this. We're going to do the limit as n approaches infinity. Same degree, so the ratio of the leading coefficients is 1/2, and that is a positive finite number. It's greater than 0. So we can say by the limit comparison test, that our series that we were looking at, the original one, must diverge. Okay, and we had already said up here that the nice one diverged and why it diverged. You need to make sure you have that somewhere in the question, telling which it does and why it does it, before you say by the limit comparison test and what the other one does. So I'm going to switch the slide. If you need to sub the pause it, just shout out. Okay, if we had this one here, we'd maybe compare it to 1 over n squared. Well, notice if we put 2 in for n, we'll get 1/4 in this one. And if we put 2 in for n here, we'll get 1/3. This converges, so we would need something that's always smaller than it. And 1/3 is bigger than 1/4. So we'd want to stay away from direct comparison. So we would want to think limit comparison. If we divided the two, they have same degree when we do limit as n approaches infinity. 1 divided by 1/2 will give us 2, which is a positive finite number. So we can say by the limit comparison test, that original series does converge because our nice one also converged. I'm going to switch the slide. If you need the sub to pause it, just shout out pause. All right, so our last example for today. So we want to know, does this series converge or diverge, which is what we're always looking for. Okay, this is pretty complicated. It looks like it might be hard as to what we should compare it to. A good rule of thumb is you should compare it to 1 over whatever the gap is between the numerator highest degree and the denominator highest degree. So notice on top our highest degree is n to the 1/2. On bottom we have n squared, so that's a gap of 3/2. So we should compare this to 1 over n to the 3/2. Now right here, notice what I was doing is I was just checking for nth term test. But the degree of the bottom is greater, so this went to 0. Because if this didn't go to 0, then, well, great. We already would know it diverges by the nth term test. But it goes to 0, so we don't know that. So we know our series 1 over n to the 3/2 converges by p series with p greater than 1. If you divide by this 1 over n to the 3/2, that's the same with keep, change, flip of multiplying by n to the 3/2. So when you multiply that through, notice now we get the same degree. So we kind of forced this to happen by doing 1 over n raised to whatever that gap is between the numerator and denominator degrees. So then we can essentially use our idea that if we have the same degree, it's just the ratio of the leading coefficients. Okay, so we're kind of clever to force that to happen. So 4 over 1 gives us 4, which is a positive finite number. So we can say, this is a really bad 1 here, but limit as n approaches 1 to infinity of our original limit, we would say converges. Okay, so that's it for this video. If there's any time left in the period, you can grab one book for your group off the shelf and you can start working on some of the homework problems. If you need more time to copy this slide down, you can have the sub pause it right here so that you have more time to copy that down.